Сейчас, прошу прощения, посудомойку выключу. Когда включаю экран. Okay. So I'm going to talk.
С Никитой возникла, Никит, простите, проблема.
Да.
Как на русский язык перевести слово towards?
Да, в направлении.
Ну, по направлению, да. Но тут же с вам мешается как-то. Вот, нет
Русскому
хорошего
человеку
русского
сам
перевода.
мешает.
Ладно.
Израиль Моисеевич учил к вопросу «о».
К вопросу «о». Хорошее предложение. Хорошо, все.
Okay, so I'm going to talk about the attempt to classify Lefschetz thimbles in field theory, specifically in two-dimensional Sigma model. And so I'll try to report on some of the progress we made recently with Igor and earlier works which are listed here. So, the idea goes back to the study of finite dimensional exponential integrals, where you have some real manifold X and some measure and some function, and you want to study the asymptotics or simply the analytic properties of the integral of exponent of some function S on this manifold X, which may depend on some parameters T, and we single out the coefficient in front of this function, which we call H bar. So the question is, what happens? So what are the properties of this integral as T and H bar are varied? So it turns out that it's convenient to view this integral as a linear combination of periods of a top degree analytic form over middle dimensional cycles in the complexification of the variety X. So if you think of the original manifold as sitting inside some complex variety, then we can decompose the X as the cycle which is represented by this real manifold X in the basis of the appropriate homology theory. So this is the relative homology of the manifold XC, which is the complexification modular the subset where the expression in exponential has, let's say, very large real part. So where the exponential itself is very small. So the point is that we want to integrate over non-compact spaces, but we choose the contour of integration so that integral converges, hoping that the measure doesn't go up too much, and whatever asymptotic behavior of the integrand is governed by the terms in the exponential.
Question.
It's a question.
What does it mean to complexify? Yeah, question. What does it mean to complexify a manifold? I mean, if manifold is you assume it analytic to begin with, or?
Yes. So I'm assuming that X is a real analytic manifold, and
okay.
So even well, it's it's not very.
Okay.
There's no canonical notion of complexification of the manifold. So in fact, any complexification would do. So maybe there might be better some complexifications may be better than others.
So maybe you have a complex manifold and then X is just some real slice in that. Is that better to say?
Yes, yes. In fact, we actually can enlarge this. So there is now, I mean, as long as X is embedded and you can deform the contour, so I think you're okay. So any complex manifold Y will do. In fact, that it's complex is just, it's also a matter of convenience. It's just that on complex manifolds, we have a simple way of producing closed forms of middle dimension. If a priori Y could be any ambient space, and it's just that we want to interpret this measure dx as a restriction of some closed form defined on Y. So if Y is a complexification of XC, and we just take the analytic form and let it continue as a complex analytic, then that gives us a closed form. But there might be other ways of extending the integrand. Anyway, so the point is that we just want to view this relation in homology, and so write X as the class of X in this appropriate homology theory expanded in some basis. So gamma A is the basis of this relative homology group. Well, and then so instead of one integral we began with, we now have many integrals to study the periods of this analytic continuation of the original integrand over the cycles gamma A, relative cycles gamma A. And the question is how to choose this. Is there a preferred choice of basis? And in fact, it's also a classic subject. So one method of producing the cycles is to start is to follow the steepest descent method. So where you start at the critical point of the function S extended to this complexification XC, choose some Hermitian metric on this ambient space, and run the gradient flow of the function real part of S divided by H bar. So you look at you take the union of gradient trajectories which emanate from a given critical point. And so because of the analyticity of this function S, first of all, the critical point of the real part of S over H bar is the same thing as the critical point of S. And then the analyticity of S would imply that if the critical point is isolated, it has the Morse index equal to the dimension, the real dimension of the original manifold. Right, so this is the local picture. If your function is just the sum of squares, which by Morse lemma you can assume it is by change of coordinates, then assuming H bar is real for simplicity, then the real part of S over H bar is the difference of equal number of squares of real and imaginary parts of the variable. So you have the Morse cell of trajectories along which the function grows. So this is where beta is equal to 0. So that's a red set in my picture. So this is what I mean by the trajectories which emanate from the critical point. So these are and there is also a dual cell which consists of the trajectories which are attracted to to the critical point. So locally, this would be the trajectory sitting at alpha equals to 0. And so they would form the dual Lefschetz thimble. So Lefschetz thimble is what you get by starting at the critical point and just following gradient trajectories in the direction of growing real part of S. So this is Lefschetz thimble L A associated to the critical point A. I think I called it gamma A. And then there is a dual. So gamma A. So the dual Lefschetz thimble would be a nice, would be a good cycle for the integrand with the reverse sign of the Planck constant. Now, what's the use of a dual cycle in the problem of integrating the what we wanted to integrate originally, namely to the minus S for each bar? Is that the intersection, if you can compute the intersection number of the original cycle X with a dual Lefschetz thimble, that would give you the multiplicity with which you take the period of the corresponding Lefschetz thimble.
Sorry.
So,
question?
Say again?
Could I please say, so the dual symbol is an element of which space?
So the dual thimble would be this element of the, eraser. So this lives in dimension X, E.
Thanks.
Okay, so just as a side remark, so that this integer number, in the finite dimensional case, it's an integer number, this NA, its computation is I think it's a partition function of some topological field theory, which one should study, in addition to the problem which I'm going to present today. Okay, so what this all motivates is it motivates the need for classifying basically the critical points of the analytically continued expression in the exponential, because the type of analytic function that your original integral is, so this guy, it's roughly speaking, it's a solution of a system of differential equations whose rank is at least the number of critical points of S. So as you vary the parameters T, the monogamy of this function would probably take values in the vector space spanned by the critical points. So that's why it's step 0 of the analysis of this integrals. Okay, so one example which we can briefly review is the way how this ideology might work in the context of quantum mechanics. So in quantum mechanics, you study among other things, you study the spectrum of the Hamiltonian, which is the Hermitian operator acting in some Hilbert space. And the way to encode the spectrum is in the character, in the trace of the exponentiated Hamiltonian. It's this object here is sometimes called the Euclidean time evolution operator. In fact, it's so this is a function, it's an analytic function of the parameter beta, which we can take to be a complex number. Well, in nice quantum mechanical situations when the spectrum of the Hamiltonian is bounded below, it is expected that this trace makes sense when the real part of beta is positive. But in fact, in order to make this exponential operator a nice operator acting in Hilbert space of quantum mechanics, not nice, but the unitary operator, the unitary time evolution, you actually want beta to be purely imaginary. And that's somehow at the border, at the boundary of the naive convergence of this trace function. So anyway, if we only want to learn about the spectrum of the Hamiltonian, we just need to know this function of beta in some domain in some complex domain. So then we'll recover the eigenvalues by some integral transform. Now, if your quantum mechanics is a quantization of some classical mechanical system with phase space P, then there is a well-known path integral representation for this trace, which you can read about in the Faddeev-Slavnov textbook, which is the integral over the space of loops. So X here is the space of loops, that is the maps, the parameterized, so the maps of a circle into the phase space. And normally physicists say that these are the loops of length beta, so that your trajectory is parameterized by a real parameter t, and the trajectory is assumed to be periodic with the period beta. In that formulation, it is kind of confusing what should happen when beta becomes complex. Oops. As I was tracing before. So it is better to change this definition to the definition where t the time actually has period strictly 1, and beta is simply coefficient in front of the Hamiltonian. So the integrand has formally the form of the exponential integral we discussed before, with the term in the exponential having both the real and imaginary part. So the real part for real beta comes from the Hamiltonian. So this is the real part. And the imaginary part coming from the symplectic area of the well, it's if the symplectic form is exact, it's just the integral over the canonical one form along the loop. If it is not exact, then usually what you say is that you take any disk. So you assume that the trajectory is in trivial homotopy class. Then you find a disk which fills this trajectory, and then you integrate the symplectic form of the disk. And then in order for the symplectic area to be independent of the choice of this disk, you impose some quantization condition in symplectic form. To some extent, many of these things can be relaxed, but let's not get too distracted. Anyway, so the point is that in this way, my manifold X over which I'm integrating is canonically associated to the phase space. It doesn't. So I've removed the dependence of beta. It is just the space of loops of size 1. Okay, I did something. Okay. Then I just need to study the exponential integral of the form we discussed in the context of finite dimensional integrals. So, well, one example where it is that the study of that integral produces an interesting unexpected result is the problem of the spectrum of the anharmonic oscillator, where we have a particle in double well potential moving in one dimension. And that's interesting because classically you expect two copies of the same physics at low energy. So one is the physics associated to the motion of the particle near the right minimum of the potential, and another one is when it moves near the left minimum potential. So classically, if you look at the phase space, you have two regions of relatively small energy, and there is an exact symmetry, parity symmetry P, which takes xp to minus x minus p, so that maps one region to another. Moreover, quantum mechanically, if you try to solve this problem in perturbation theory in the parameter h bar, you will indeed find two exactly identical perturbative series for the eigenvalues and for the eigenfunctions, which will be supported near the respective minimum. So that way you would conclude that your trace, so that this trace has the form 2 times some series. So you have the sum of exponentials with coefficient 2. And similarly, if you consider the twisted trace, so you could insert the parity operator under the sum of the trace, but the same naive perturbative considerations would tell you that this is equal to 0, because you have the exact degeneracy of the levels. Now, if you read Feynman's lectures on quantum mechanics, you'll find that you can estimate this. You can estimate the ground state energy by making some variational estimates with various test functions, and from that you can conclude that you cannot have. The ground state energy cannot be degenerate. So if you had these two delocalized wave functions, one psi minus and one psi plus, you can find a linear combination of those functions which would have the value of this integral smaller than the eigenvalue you had. So that means that you can reduce the eigenvalue, therefore it means that the ground state energy is actually smaller. So it means that there is something wrong with the perturbation theory, and indeed the exact result is non-perturbative. So it is not analytic in H bar. It contains terms which cannot be whose Taylor expansion gives 0 to all orders, but they're actually non-zero. And so this is usually demonstrated by making again some sort of saddle point estimates of the path integral, usually not the path integral which computes the trace, but rather the path integral which computes the transition amplitude from let's say the point x equals to v to the point x equals to minus v, which in the phase space language means that you look at the maps of the interval such that the endpoints of the interval map to two Lagrangian submanifolds in your phase space. And well, I will, okay, let's see. So usually, okay, so this is, maybe I should not review this too much. This is where people come to the notion of instantons and anti-instantons. So if you look at the expression which we have in the exponential, and we look for the critical points of the expression in the exponential. Well, these critical points are essentially the solutions to Hamilton equations, except that we have some extra factors of I and beta here and there, because we slightly change the form of the canonical action from which usually the Hamilton equations follow. So this is the usual action from the textbooks on classical mechanics, from which the usual Hamilton equations follow. But here we multiplied the first term by I and the second term by beta. So that's why we get an extra prefactor. And I think for simplicity, I redefined my beta. So what I used to call beta over h bar is now called simply beta. So these are the equations which you want to solve now. So as you can see, they're obtained by straightforward variation of this action. Now, what textbooks do, they solve the first equation for the momentum implicitly. They don't, so they solve it and then substitute into the second equation. And so they get the Euler-Lagrange equation for the inverted potential. And somehow the fact that the momentum, which corresponds to the solution of the first equation, is purely imaginary if the coordinate is real, that fact is usually overlooked. But I want to stress this fact now that already at this stage, without even knowing, we are talking about now the complexified loops, so or the map or the complexification of the space of maps of the time interval into the phase space, because from this equation it follows that you cannot have both P and Q real. So something has to become complex. And moreover, well, so then people say that, well, we're only interested in the solutions when beta goes to infinity. So this is the question of the ground state. And when beta is very large, the exact solution to these equations can be approximated by the solution which takes an infinite time and takes you from one maximum of the inverted potential to another maximum. So that's the transition from the top of the hill to the well, and then back to the top of the hill. So that's the instanton solution. And then that's not enough. So then people say that, well, there are many more solutions which were for a long time. By time I mean the Euclidean time. The solution just stays near left or right minimum, so near V or minus V, and then transitions between these 2 points in a relatively short time, and then goes back. So these are these combinations of instantons and anti-instantons. And then by some plausible hand waving, people arrive at the computation of the splitting of the energy levels, which is due to take into account these transitions between two critical points. So maybe I made it sound even less convincing than it should be, but it does sound a bit fishy that we are not, we're doing something strange. Whereas what we should be doing, we should be looking for two critical points, And one lesson which we need to, which we could take from the previous discussion is that these critical points most likely will be sitting in the complexification of the loop space, which I take to be the loop space of the complexified phase space. So these are now my maps of the real time. Into the complexified phase space. And so the Lefschetz thimbles, which would be associated to the two critical points, which are now the solutions, the periodic solutions of Hamilton equations, of these modified Hamilton equations, where I'm allowing P and Q to be complex. But I insist on the time periodicity. Now, so here I was looking at the problem of computation of the trace of the Hamiltonian, and that's just, so that corresponds to the integral over the loop space. One can also study twisted traces where G is an element of some global symmetry group. So it's a symmetry of the Hilbert space and Hamiltonian. And now in the so in the case when G is realized, it's a unitary symmetry. So that's what I mean by the symmetry of the Hilbert space. So then, and your phase space, and sorry, and the quantum system is the quantization of a classical system. Then, essentially, this trace would be given by the similar integral over the space of twisted loops. So twisted by the conjugacy class G. So these are the loops for which the time translation by one is equivalent to the symmetry transformation. But then, just like with the parameter beta, which here we can make complex, and that's how I made it complex by simply moving it out of the integral and making time just a parameter taking values between 0 and 1. So whereas for the unitary twist G, there are two representations. Okay, there is either representation using the same integral but with a different domain of integration. So here I'm talking about twisted loops as opposed to the ordinary loops, or I can rewrite it in a form which then would allow me to complexify G. So this can be also written as the integral over the ordinary loop space. But then, in addition to, then I would modify the action. And if G is a Lie group, let's say it's a Lie group. Otherwise, it doesn't. So, okay, there are two interesting cases. So, the one case is when G is a discrete group. Then I'm just using this representation, and I don't bother about any complexification because what does it mean to complexify discrete group? But if G is a Lie group, then it makes sense to complexify it. And so before I complexify it, I represent G by, well, I present the Lie algebra by the moment map. So by the Hamiltonians, we generate the action of the algebra. And then I introduce the gauge field. So it's one-dimensional gauge field on the circle. So it's a G-valued gauge field on S1, and then minus again beta H. And now this can be complexified, and beta can be complexified. So in this way, we get an integral representation for the analytically continued trace, which is important for some applications and will be crucial for what we will be discussing later in the sigma model context. Okay, so now the special feature of the anharmonic oscillator is that it's a particular example of the so-called algebraically integrable system. So that's a feature which you see once you complexify the phase space. And so what do I mean specifically here is that the level set of the complexified Hamiltonian is actually an elliptic curve, minus maybe 2 points, but the general structure for which I want to present some kind of universal answer is the structure of, so I'm assuming now that my phase space upon complexification becomes an algebraic integral system. So it has the structure of the fibration over some of a fine complex manifold of dimension equal to the real dimension of the original space, with fibers, so Lagrangian, it's a Lagrangian fibration, so the fibers are Lagrangian submanifolds, and I want them to be abelian varieties. So generically, I want them to be, so maybe I will partly compactify my phase space. This actually goes back to the original question of Andre. I mean, what do I mean by complexification? So I'll allow for some partial complexification, for example, so I can add some points so that my fibers will become compact abelian varieties, which I allow to degenerate somewhere over the base, so there's discriminant locus. And now in terms of this structure, so I have a base B, which let me say it's just C to the R. R is the real dimension of P, my original phase space. And now it turns out that the a priori infinite dimensional problem of classifying the Lefschetz thimbles for this class of quantum mechanical systems actually reduces to a finite dimensional problem of finding a critical point of some analytic function, essentially on the spaces which are.
Sorry, Nikita, half of the dimension of your phase space.
So R.
R.
So R is a half of the dimension of my phase space. Yes, you're right. It's half of the dimension. It's half of the real dimension of P. Yes, thank you. Indeed. So P itself has even dimension, which, okay, so, and that even dimension of P is equal to the real dimension of B. So maybe that's what I want to say. So B, so the original phase space somehow, since it's it's like a half of B and half of the fibers over B, over that half. Okay. So that half is kind of physically important, that it's only half. Okay, so well, what's next? Well, we still need to solve these equations, the Hamilton equations, and now that I assume that my phase space, the complexified phase space, is an algebraic integrable system, I can solve it. I can solve these equations in the coordinates, in the nice coordinates, which the integrability gives me, which are the action angle variables. So the action angle variables are, I will denote them by A and phi. So A's are local coordinates on B, and phi's are coordinates on the fiber, which are normalized such that, so that half of the periods are essentially the integers, 2 pi times an integer. What's unusual in this complex case compared to the real case, of course, is that the abelian variety A sub B is it's a complex torus, so it's the quotient by the 2 r-dimensional lattice. And so in addition to the A periods, it also has B periods, which are integer multiples of some complex numbers organized into the period matrix. Okay, so we all know that structure. That's the same structure as in special geometry of n equals to gauge theories in 4 dimensions. But now let's go back to the Hamilton equation, just solve these equations, which is now a complete triviality because the Hamiltonian only depends on action variables. So action variables stay constant in time, and the angle variables, the angular velocity is also constant in time because it's given by the derivatives of the Hamiltonians with respect to the action variables. So the solution is very simply just a linear function, and all we need to ensure is that our solution is time periodic, because we still, we have to find the periodic trajectories. Now we know that since A is constant, these trajectories sit in one abelian, in one fiber. But now which fiber can support such a periodic trajectory? Well, that we will find if we remember that we need the trajectory to be periodic in time, so that if time t is shifted by 1, then the difference of the angles should be a period. So it should be equal to the ambiguity of definition of phi. And that ambiguity has 2 integer vectors, A periods and B periods. And so we arrive at the following conclusion, that this combination beta h over I times the derivative of the Hamiltonian with respect to the action variable should be equal to the integer 2 pi times an integer plus tau times the second integer. Now, this condition can be rewritten as the condition of having a critical point for the so-called superpotential function, which can be invariantly written as simply the period of, so the canonical period, the period of the canonical differential over a cycle in the fiber, minus beta times the Hamiltonian, which is a function on the base. So for fixed gamma, so gamma here, so gamma here is a discrete variable. It's an element of the lattice, which is the lattice of the first homology of the generic fiber. And then once you fix an element of that lattice, you get a certain discrete subset of the base, which is the subset of the critical points of the function, which depends on the choice of gamma. So that these equations are equivalent. So the bottom line is that this is a finite dimensional problem. For each gamma. And moreover, this problem looks like a problem of classification of Lefschetz thimbles for the finite dimensional function, which is this superpotential W. This is not to say that the Lefschetz thimble for the original quantum mechanical problem is equal to the Lefschetz thimble of this auxiliary Landau-Ginzburg type problem, but they might be related in an interesting way. So maybe, one option, one possibility which I consider to be quite promising is that these Lefschetz thimbles of this function W gamma are good starting points for doing perturbation theory for the infinite dimensional problem of computing the path integral. Okay. Now lots of examples of algebraic integrable systems are given by families of algebraic curves. Well, in the case of the anharmonic oscillator we start with, that was just by the one-dimensional nature of the problem. But as you know, many interesting systems can be viewed as limits of particular cases of, for example, Hitchin systems. And for those systems, these abelian varieties are Jacobians or prime varieties of speckle curves. And so this superpotential, which I described in terms of this abstract abelian varieties, can be described even more concretely in terms of the periods of some differentials on the family of curves. And so that looks like more like a separation of variables type of statement. Okay, so now armed with, yes, oh, sorry, I should have finished relating. So finally, by exploring these families of the solutions of these equations in the case of the anharmonic oscillator, one finds the correspondence between these exact critical points, which are labeled by two integers. Because we have so here we have an elliptic curve, and so we have these possible cycles of the periodic trajectories are labeled by two integers. Physically, these two integers represent the number of tunnelings under the potential, under the hump of the potential, and the number of the classically allowed oscillations near either one of the minima. So in that sense, one of these integers is like it's a proper number of instantons, anti-instantons, and another integer is like it's a number of perturbative oscillations. But the point is that the exact saddle points, the exact critical points of the action are nonlinear superpositions of the instantons, anti-instantons, and perturbative and oscillators. So this is what the textbook analysis doesn't see for some reason. But if you read Coleman, for example, his Erich lectures on uses of instantons, he has some vague statement to the fact that, well, these true critical points are somewhere in the field space, hopefully not very far from this cooked up trajectories which we use for the evaluation of the path integral.
Question.
Yes.
So suppose I have a motion in some arbitrary polynomial potential.
Yes.
Not degree 4, but some, right? That's classically integrable because it's just 1 degree of motion, 1 degree of freedom. But not algebraically integrable because your curve will not have a genus 1. Is can you explain what goes wrong with this? What would be the difference with the picture you explained here?
Well, I'm not saying that I exhausted all. I just present the solution for the restricted case for the class of problems. So the motion in general prenormal potential simply doesn't fit that class, but nevertheless can be probably analyzed. So you can, so one way to think about it, to map it to this class of algebraically integrable systems is to study the motion of not one particle in the polynomial potential, but k particles, when k is actually it's a genus of the corresponding hyperelliptic curve. So in that way, you can actually artificially make it into the algebraically integrable system. But qualitatively, what do you expect? You expect that in that case, the true saddle points, the critical points of the complexified action would probably be labeled by 2G integers, where G is the genus of the corresponding curve. It has some genus G, and you have 2G integers. And so some of these integers, again, you can qualitatively understand as describing the tunneling between different minima, and the others will be corresponding to this perturbative fluctuation. So that in that sense, that picture would probably be similar. Now, again, you can solve of course you can solve the Hamilton equations, and so what's missing in this case for me is that so you can the periodicity condition, which here I had two ways of formulating. So one was simply saying that the period of some differential is let me see. Yeah, I don't. So, okay. So basically, so you have the genus G curve C, and the trajectory will be again, of course, will be sitting on this curve. So it will represent some integral cycle, and the condition for this curve yes, I think I remember yes, now I remember. So the problem is that you need to fix many parameters so here you have one parameter at your disposal, the energy, but of course the family of curves which you get is so what I want.
No, you want to fix.
I apologize. I didn't mean to make it a long discussion. I thought they had a simple answer. We can discuss it offline later. Yeah.
Andrei, one of the possible answers is one-dimensional system is integrable by Liouville, but it's not algebraically integrable. The complexified level of
yes, Igor, that's right. But that's what Andrei was asking. So what goes wrong? That was his asking.
The wrong is that it's integral by Liouville, but it's not algebraically integrable.
Yeah, but I was asking how we're gonna see that in the final answer, because in the final answer where kind of things tunnel from one minima to another minima. What would this what will we see something different qualitatively, or will we see the same picture? That was and we can discuss this question later offline.
A part of the things, Nikita, you wanted to say how you fix these other integrals of motion. Other modes.
Well, there is one equation. So we have one parameter, which is the complex energy level E, and we fix it by requiring the period of the holomorphic differential dx over p over the specific cycle gamma to be equal to beta, or maybe my units is that. So E is determined by gamma and beta. So beta is complex number, gamma is a cycle. So it's just some transcendental equation. It's the nice feature of the algebraic integrable case is that so that in general then you would have several. Maybe so in the integral case, actually, what we study is not just it's not just a trace of the Euclidean evolution operator. We actually study the generalized Gibbs partition function when we have all integrals in the generating function, and so there so there you have more control parameters, so to speak, and so then the equation turns out to be that the kth holomorphic differential, the period of the kth holomorphic differential is fixed in terms of beta k. So here, I mean, we don't ask this question because we only have one Hamiltonian, and in principle, I mean this equation is as good as all other equations. So one can study it on its own. It's just that in the case of algebraic integrable system, there is a way to rewrite this equation in terms of this critical, as a condition for the critical point of some function, which requires some, it requires a little bit of playing with differentials, which is, well, I think it's a nice condition that, it's one thing to say that you're looking for some solution of some transcendental equations, and another thing to say is that you're looking for a critical point of some function. So in that sense, the algebraic integral case is of course nice. But as I said, even this case can be made into the algebraic integrable case by making it by studying a many-body system, where you study the motion of G indistinguishable particles in this potential. So then this is all. Oops. So then you replace the original phase space by its Hilbert scheme of G points, and that's an algebraic integral system. Okay, so field theory. So the field theory, which I want to apply this where we want to find the analog of this structure, is the sigma model. So it's the theory of maps of Riemann surfaces into some target space, which we will take to be a sphere. And so in this case, we have a symmetry, which is it's a round sphere. So we'll have the symmetry of rotations. And that's why it's usually called the ON model, because of the ON symmetry. Now, this is also a textbook example of the spontaneous symmetry breaking and restoration. So if you do the naive analysis of maps of some Riemann surface into the sphere, and then you expand around the maps to a point, then it looks like, so for each choice of this point on the sphere, you have a vacuum of the theory, and then around this vacuum you have n-1 massless fields which describe the tangent space to the sphere at this point. Valued massless. This is the illustration of the Goldstone theorem, where the choice of X breaks the ON symmetry down to its subgroup, ON-1, and then therefore you have the massless fields which are the Goldstone bosons for that symmetry. But then there is another theorem which says that in 2 dimensions you cannot have a spontaneous breaking of continuous symmetry, so that this massless Goldstone bosons will actually, because of the logarithmic nature of the Green's function in 2 dimensions for massless fields, the fluctuations will actually be so strong that they will somehow make transitions between different points. So the different points of the sphere will not be orthogonal vacua of the theory. And so then you can argue, by at least in the larger limit, that the vacuum is ON symmetric, and the expectation value of the let's say linear embedding coordinates is actually equal to 0 in the true vacuum. Instead, you have no massless fields, and this theory is believed to generate the mass gap, even though classically this theory is conformally invariant, has no mass parameters, but it is believed as quantum field theory, it has a dynamically generated mass scale. And so the study of this model is actually important for more realistic questions like confinement and mass generation in 4-dimensional QCD. So that's why it would be nice to have a kind of more rigorous treatment of this model. And so we would like to start with properly formulating the classification problem of Lefschetz thimbles in this case. So again, to explore the symmetries, to detect the symmetries and detect the violation, we would like to introduce the twisted character, where we would be studying the theory which is quantized on a space of finite size, so in a circle. And to this, one associates some Hilbert space, H of S1. And then in this Hilbert space, we have several interesting operators acting. Well, first of all, there are operators of the group ON. So let me just describe maybe the sphere so that it will be clear what is the ON. So I view the sphere as n-1 as sitting aside Rn. So it's a set. That's my sphere, and ON acts linearly on X. Right, so now we have a Hamiltonian H hat, and we have a momentum. So the momentum operator translates space. So if my space is parameterized by variable x without index, so x plus 1. And then the Hamiltonian is a time translation, but of course it's realized in terms of the as an operator acting on the space of wave functions or wave functionals. Okay, maybe I should go back to, so I will So apologize. So I will use sometimes the notation sigma for space, and sometimes I will use x, depending on convenience. So here, in order to not to be confused, not to confuse the worldsheet and target space, I will denote sigma for spatial coordinate, and x vector is the target space variable. Okay, so so the Hilbert space consists of some functionals of loops taking values in the sphere, and the novelty of 2 dimensions is that in addition to the twist in time direction, like here, which if I rewrite it in terms of the x vector, I will write as follows. So x vector of sigma t plus 1 is equal to g acting on x. So in addition to the time twist, which is here, we can also impose the space twist. So in this way, one actually defines a new type of Hilbert space, the twisted. So it's a space which is obtained by quantizing the twisted loops. So in this way, I'm actually explicitly breaking the ON symmetry down to the subgroup of ON which commutes with H. Why is it interesting? Well, that's because, among other things, if you study the modular transformations of this trace, of course, this time twist and the space twist will get switched. So that gives you better control over the theory. So if you know the dependence of G and H, but then of course you can take the limit when H goes to 1. But it might be that for to analyze the dependence of, so to compute this partition function for generic G and H might be easier than to compute it first for vanishing twists. Okay, so this is nice, and so we can for G and H taken values in the group ON or NR. This is essentially the path integral over the space of maps. So X is a space of maps of the torus, the sphere, which are HG twisted in this sense, and so we just compute the Dirichlet. We put in the exponential the Dirichlet energy of the corresponding map. Now, this can be represented using the embedding of the sphere and in the vector space in a convenient form using Lagrange multiplier enforcing the constraint. So this is essentially the energy of the map into the flat space plus the Lagrange multiplier enforcing the constraint defining the sphere. And now in this form, it is trivial how to complexify the model. We just make X complex valued and U, the Lagrange multiplier, complex valued. We preserve the wall sheet to be real two-dimensional torus. Now, as in the quantum mechanical case, so again, remember in quantum mechanics we had this parameter beta, which was the inverse temperature or Euclidean time, and actually it was a complex. Naturally, it was a complex parameter. So similarly, we expect this complexification in the two-dimensional case, but remember that now we have two operators in the exponential. We have the Hamiltonian and we have the momentum. And so actually we expect both beta and theta to be complexified. In other words, if I form the usual modular parameter of the elliptic curve represented by the torus, the Walsh torus, then now I have independent tau and tau bar. So they're not complex conjugate in general. And so just like I explained in the quantum mechanical case, we can just make the action to be written as an integral over the torus given by coordinates x and y with periodicity 1, but then tau will enter the kinetic term. Tau and tau bar will enter the kinetic term in a specific way. Okay. So now we can go from the original real variables x describing the vector space, and let me assume now for simplicity that my ambient vector space is even dimensional, so that the sphere I will be talking about will be odd dimensional. And now it is convenient to pass from the metric written in terms of the usual Euclidean metric dx squared. I can rewrite it as the so this is the kind of a Minkowski rewrite it in terms of light cone coordinates, except that now everything is complex. So I have coordinates light null coordinates z and null coordinates z tilde. So these coordinates are singled out by my choice of twists. So this is my definition of the basis for these null coordinates. So the z under the time shift is multiplied by some complex number GA, and z tilde is multiplied by the inverse. And similarly for sigma variables, for the space shifts. Okay, let me rewrite it now that I passed from x to z, I can actually write it in terms of x. Okay, and so this is roughly how tau and tau bar enter my action. So now, so sigma and okay. So this is x, y, x, y, x, y. So the integral is over dx dy. So xy live in the square two-dimensional torus, but the action depends on additional complex parameters tau and tau bar. And these twists, now h and g are complex. So again, we can either say that the fields z and z tilde are twisted, or we can say that they are periodic, but instead add additional terms to the action involving the gauge fields. So we can promote these derivatives to covariant derivatives with a flat connection. Okay, so now so the problem now becomes, so to find the critical points now becomes the problem of finding a so-called self-consistent Schrödinger potential on the two torus. So this is our Lagrange multiplier. Which is doubly periodic, because with all the twists were making the fields quasi-periodic, but the constraint on these fields, namely Z A tilde, the sum over A from 1 to M equals to 1, that constraint itself is doubly periodic, so it needs the periodic Lagrange multiplier. Now I will switch notation again from Z to psi because of the Schrödinger potential. Usually we denote the solutions of Schrödinger equation by psi. And so we need the Schrödinger potential on the torus such that it has 2M solutions, which split into the pairs of basically dual solutions. They are dual in the sense of the formal self-duality of the Schrödinger operator. So it's a second order, it's sort of a self-adjoint operator, except that now the notion of adjoint doesn't involve complex conjugation. And so the dual solutions have dual twists. And very conveniently, our fields in a sigma model also split into such pairs. So basically, we want U to be such that it has 2M solutions with prescribed Bloch-Flaquet multipliers, GA, and the inverses, such that the potential itself is expressed in terms of these solutions, or not, so that the solutions are normalized. So this is and from that you can easily deduce that U is equal to TZ psi. So this is the cell consistency that the Schrödinger equation is, the Schrödinger potential is such that it is expressed in terms of the zero eigenvectors of the corresponding Schrödinger operator. So the question is how to find such potential and solutions. So the idea is to first look at the space of special Schrödinger potentials, which are in some sense, it's kind of a nonlinear generalization of the trigonometric polynomial, so finite number of Fourier modes. So basically the logic is that, okay, so we have this field theory, which is maybe you can view it as infinite dimensional version of the quantum mechanical problem. So it's now not one particle, but infinitely many particles moving in some complicated potential. And so what we are hoping for, we are hoping to find the critical points of that infinite dimensional problem within some finite dimensional submanifold in the infinite dimensional manifold of all possible configurations. And then we will try to, well, if we're lucky, then these finite dimensional submanifolds, maybe they will have growing dimension and they will exhaust for all practical purposes, they will approximate all solutions of the original infinite dimensional problem. Now, so part of our structure is this Schrödinger potential, which accompanies every solution of the sigma model equations on two torus. So we can try to classify the complexity of the solution by the complexity of the corresponding potential. So a naive classification would be to say, well, let's look for the solutions for which this Schrödinger potential is just a finite number of Fourier modes. So that would be, so that would be like saying that I will approximate my infinite dimensional continuum problem by some lattice approximation. So for the lattice will give me a finite dimensional approximation, which is sort of similar to the approximating any doubly periodic function by trigonometric polynomial, by Laurent polynomial in exponentials. Well, it turns out that, of course, this is too naive.
Is it obviously consistent with your constraint that the potential?
Absolutely not. No, absolutely not. So that's why this is a bit too naive. But it turns out that there is a slightly nonlinear correction to this naive prescription, which turns out to be consistent with the constraint and everything else. And that's the notion of the finite gap potentials. And so in order to define what are the finite gap potentials, so let me just, so it's nonlinear version of kind of lattice approximation is the finite gap potentials. So to define a finite gap potential, I need to define an auxiliary analytic object, curve. Now it's complex analytic curve. Which is defined as follows. So given the Schrödinger potential, and of course, given tau and tau bar, which is also part of structure. So we look for the space of Bloch multipliers. In other words, we look for flat C-star connections on two torus for which there is a non-singular solution of the Schrödinger equation with given multipliers. So it's a set of A's and B's such that there is a solution with given potential U with the quasi-periodicity determined by A and B. So that gives me so this is inside C star cross C star, and that's the highly, well, that's the curve with many, infinitely many double points. And so we take the normalization of that curve. So we resolve the double points, and we call that the Fermi curve. It's a Fermi curve because it has to do with Fermi level in one particle approximation for the electron wave functions in the crystal. But it's also, again, so it's complexification. So A and B are complex numbers here. So to get the feeling for what this curve is, let's look at the special case when the potential is a constant. So potential is just a constant. Then it is easy to solve the equation, the Schrödinger equation. The solution is just the exponential function, where z is x plus tau y and z bar is x plus tau bar y. Remember, tau and tau bar are complex numbers, which are not necessarily complex conjugate, but so the fact that this plane wave solves the Schrödinger equation imposes the constraint on the momenta, so the coefficient in front of z and coefficient in front of z bar. So the product is equal to u0. So so this way you get the solution. The wave function is a function of z bar and the auxiliary parameter k, like a spectral parameter, like a quasi-momentum. Now this parameter determines the Bloch multipliers by these trivial formulas. U0, sorry. Notice that formal self-adjointness of the Schrödinger operator, which I mentioned before, leads to the involution of the curve of the parameter k which inverts simultaneously both Bloch multipliers. So k goes to minus k, and that's maps A to N inverse and B to B inverse. Okay, so what we have a map of the line, complex line with the parameter k to the algebraic torus C star cross C star. So this is the k line, and it maps by these formulas. So we get a map into the two-dimensional torus, and what you can easily check by solving the equations in this rectangle, that this map, the image, will have infinitely many double points. In fact, this image looks like a kind of a lattice, a two-dimensional lattice. So you have, basically for every pair of non-zero integers, you have a solution to this equation. And so that this equation describes the double point. So 2 points on the k line, which are mapped to the same point in this modular space of flat connections. So the normalization in this case simply means just going back to the k variable, so that the normalized, so the Fermi curve for the constant potential, non-zero, I should say, non-zero potential, is just CP1. So or CP1 with 2 punctures, without 2 points, k equals to 0, k equals to infinity. Let me call them p plus and p minus. And notice that these points are invariant, are fixed by the evolution k goes to minus k. So 0 and infinity are intact. And at these points, the solution, so p minus, let's say, is when k goes to infinity. So psi behaves as the holomorphic function. And at p plus, let's say k goes to 0 at p minus. And near p plus, psi goes like holomorphic function. So there are 2 points on this Fermi curve where the solutions approximate the solutions of a massless equation. And everywhere in between, this plane wave it's a wave function of a massive particle, because with the mass squared equals to u0. Okay, well, that's just a model example. So the Fermi curve in this case is just CP1, and we notice that it has this involution sigma, and it has 2 special punctures near which the wave function asymptotes to the holomorphic or anti-holomorphic function in the parameter z bar. So now, once we perturb the potential by adding non-zero Fourier modes, what happens is that the double point of that curve, which corresponded to the parameters m, to the integers m n. So this is where m and n essentially are encoded. So this is where the difference of the quasi-momenta is an integer. So such mode essentially resolves the double point more precisely, you actually need to turn on 2 Fourier modes, both umn and minus m minus n, and then you resolve simultaneously two double points. And so you create a small one cycle on this curve, and so then qualitatively you expect that once you introduce such deformation, then you no longer need to resolve any double points in the vicinity of this in this neighborhood, so that the Fermi curve will grow in genus by once you add more Fourier modes. So the definition now is that the finite gap potential is such a potential U for which the Fermi curve, which is the result of this procedure, which is the normalization of this set of A and B, is a finite genus curve. So that's the definition. So it is as if it is almost the same thing as saying that it has finite number of Fourier modes, because basically what it means to be a finite genus, at least for sufficiently small Fourier coefficients, is to resolve the finite number of double points, which will produce the finite number of handles, and then the rest of the double points which are not resolved, well, will be resolved by normalization. And maybe they will decouple. So we'll get to
Sorry, I'm a bit lost. So what's the degree of this curve? Is it infinite degree? Or has it infinitely many components?
Or
it's a finite degree?
No, I think I think for generic potential it is connected, but it is of infinite genus. So
Andrei, it's not the degree is not well defined. It's not a plane curve.
Still, I mean, it has some homology class on the torus. So is it, well, before you perturb, is it has
I don't know.
Before you perturb the normalization, is it has one component or it has countably many components?
No. It has just one component in case of U.
Before it just, before perturb it just CP1 and the normalized curve for just CP1. And its image is just, it has one component. It's a connected curve.
Okay,
so
it has finitely many nodes, for example. No, it has
infinitely many nodes. Infinitely many. You see, this torus, maybe you're confused by. You see, I cannot extend this into P1 cross P1, for example. So.
Andrei, the CP1 is embedded in the torus by transcendental map. That's why you see it's e to the power. It's transcendental. That's why it has infinite, if you wish, infinite genus as algebraic genus.
Okay.
It has infinitely many.
Okay, cool.
And it's not by accident that I drew it as a kind of lattice. It really it does look like a lattice, but of course. But unfortunately, it's a lattice where each row and column, they're all connected also. So it's not.
In some sense, it's not algebraic curve. It's analytic curve.
Yes, it is an analytic curve. It's a complex analytic. It's not. But for the finite gap potentials, we will require it to be a finite genus, in fact, algebraic curve. So that's our simplifying assumption. For the, sorry, I lost my slide. Finding a potential. Yes. Okay. This is the definition. So then the question is, okay. So we have this nice definition that we would like to concentrate on solutions for which the corresponding Schrödinger potential is a finite potential. The question is how to find such solutions. So what are the additional what are the requirements on the curve, and so on and so forth. So this is so we have some characterization of this curve. So we start with the smooth. So here is some kind of axiomatization of the structure which we saw before. There is some additional ramifications which I didn't explain, probably will not explain. Anyway, so we start with a smooth genus, let's say genus G algebraic curve with n+1 pair of punctures. So one pair will be denoted by capital P plus and capital P minus. So this is the familiar points in the example above. And additional n pairs of punctures P plus minus small. And we assume there is an involution of this curve gamma for which these punctures whose fixed set is precisely the set of those punctures. So I try to draw the picture again with the limitations of real geometry. Okay, so there is a quotient curve gamma 0, which is the quotient of gamma by sigma. And it is not difficult to compare the genera of gamma 0 and gamma by Riemann-Hurwitz formula. What else do we want? So we fix some local parameters near capital P plus and P minus, which we assume to be odd under the involution. So in the example of constant potential, so one of its local parameters was just k, and another was something like u over k. Near infinity and near 0. So then we need to fix a meromorphic differential on the quotient curve, whose poles are exactly at the ramification set. Moreover, we require that the residues of this differential at P plus and P minus are equal to plus minus 1, and the residues at this additional punctures at plus and minus point are opposite to each other. So this, you can think of this as by saying that actually these punctures are the formal double points of a degenerate curve, of a curve with nodal points. So d omega is a holomorphic differential on the curve at which the P plus and P minus punctures in each pair are identified. With the additional constraint that the residue of d omega at capital P plus or P minus is equal to plus minus 1, not anything. Now, because it has two n plus 1 pole, 2 times n plus 1 pole, it has 2 times n plus g naught, which is equal to g plus n zeros on gamma naught, so which are denoted by gamma 1 0, gamma 2 0, gamma g plus n 0, and then I choose a preimage of the zeros under my projection pi. So projection pi is the projection of curve to the quotient. And so once this choice is made, we call that the collection of these points, the admissible divisor, capital D. So we have many choices, that many choices for such pre-images. So then, once this data is fixed, we claim that for generic admissible divisor, there exists a unique function. So it's a function on curve gamma, on the bigger curve, and the function of the auxiliary parameters z and z bar, such that it is meromorphic outside the punctures P plus and capital P plus minus, has at most simple poles at admissible divisor, has the essential singularity of prescribed type near P plus which is holomorphic in Z variable, and similarly has essential singularity near P minus also of prescribed type, which is anti-holomorphic in the Z variable. And in addition, we require it to be glued, so its values at P plus I and P minus I to be equal. And so we can find this, we can express this function in terms of theta functions on the prime variety, which is one of the formulas that Igor writes in many of his papers. so maybe I should not, well, I don't know, it's maybe too late today to explain this in detail. But anyway, so this is some straightforward, from that point on, it's some straightforward construction. What's missing here is so of course, as you can guess, this function psi, and its image under their evolution sigma. So its values at special points will produce the solutions of the sigma model. And these points are the poles of the additional structure which one needs to fix, meromorphic function E. On meromorphic function on gamma 0. So it's a function on the underlying curve, so that its poles lead to pairs of poles on gamma, and they correspond to the values of dual coordinates. So this is QA plus QA minus. So this meromorphic function is an additional choice. One should supplement the choice of the curve by, and then, well, it turns out that, so from that, one proves by, again, the ingenious manipulations with residues that, well, there's some normalization factors which one can compute from the residues. So so E d omega. So remember, d omega was the meromorphic differential on gamma 0. E is a meromorphic function on gamma 0, and essentially so E plus minus are the values of E at the punctures. So by playing with differentials like E d omega or differentials like psi sigma d omega, one proves that the constraints are satisfied, and then the potential is indeed self-consistent. And moreover, one can impose. Well, okay. So all this produces what does it produce? So this way one finds the solutions of the yes. So first of all, I should have said that this Baker-Hazer function. So that's the equation that it solves. So that for each p in gamma as a function of z and z bar, it solves the Schrodinger equation. Now, what a priori is not true is that this equation is doubly periodic. It is only quasi-periodic. So there is some periodicity inherent in the prime variety of the curve gamma. And so this potential U can be written as the logarithmic, as Laplacian applied to the logarithmic, as to logarithm of theta function on this prime variety. But to guarantee that we actually have the solution on the torus requires additional constraints on the curve gamma and all other choices, so which appear to look transcendental, but remarkably can also be stated as the critical point of some superpotential, which interestingly has some similarity to the superpotential we found in the quantum mechanical case. So in particular, it can be expressed, its derivatives can be expressed in terms of the expressed in terms of the residues of the interesting differential log B d log A. So this is the modular space of the C star flat connections on the torus. So it has this multi-valued one differential. I mean, it has this canonical symplectic form, d log A, d log B. And so the Fermi curve, as we discussed, by the monodromy map is mapped to this symplectic surface. And so you get some kind of a Seiberg-Witten geometry where you compute the period of the derivative of the symplectic form around some puncture on the Fermi curve, and that defines for you, it turns out, some kind of superpotential, so that these nasty periodicity constraints can be packaged into the condition for the of the criticality of that function. So this is more or less the story for the even dimensional spheres. We have so we also have a story for the this was a story for the odd dimensional spheres. We also have a story for even dimensional spheres, which it turns out require the singular Fermi curves. And we also have the story for the projective space, and its complexification, therefore, which also formulate in similar terms. So, but obviously the story is not finished. It's just the beginning. Thank you.
Thank you, Nikita. You managed to pack in 2 hours so many new things that probably at some moment will continue this talk. Any questions?
Is it fair to ask for like what's the summary? What's the conclusion? If you could describe it in a couple of like English sentences, what is it? How we should think about the thimbles?
Okay, so maybe one qualitative. Okay, I can say. Okay, maybe first of all, what one should do. There are these famous questions: what to do and who is responsible, right? So, what should be done? So for each for each solution, gamma, d omega, e, and so on, find the determinant, appropriately regularized determinant of the second quadratic form. So this is more or less, so the problem 1.1 seems to be not out of reach of persistent researcher. The problem 1.2 seems to be very complicated at the moment, namely to find the multiplicity of this given critical point in the real contour. So that means find the number of properly regularized, find the number of the gradient trajectories starting at A and reaching real valued maps, real valued map of the torus into the sphere. So this is computing this intersection number of the real cycle in the space of sigma model maps and the dual Lefschetz thimble. So at the moment I have no idea how to approach this problem, because so the gradient trajectories, this is some kind of infinite dimensional parabolic equation, and I don't know what can be said about its solutions. So that seems very hard. And then, well, if this is done, if this is somehow achieved, then we have a good starting point for the analysis of the partition function on the torus in the presence of twists. And so from that we can try to extract the spectrum and extract the mass gap. So So where is the mass gap? So the mass gap is, in some sense, it's the average of the average value of the zero mode of the Schrödinger potential over all the solutions. So the measure with which one takes the average involves these determinants. So that's a priori it involves these determinants. So I'm not sure how one can say anything a priori without evaluating these determinants. But the expectation is that for most solutions, U0 is non-trivial, is not zero. And presumably the regularized expression for this determinant will involve some dimensionful parameter. And so this typical non-zero value of the potential zero mode will be some number times that dimensionful parameter. And so that would give me the mass gap of the ON model. So instead of the conclusion, this is I think nobody does conclusions these days. One always draws roadmaps, right? So this is a roadmap. And then hopefully one day my dream is to find a similar structure, of course, for the four-dimensional Young-Mills equations. There is one hint that this structure might be there, and that's that because there are solutions. Maybe I already talked about this. So in Young-Mills case. So the one generalization of the torus S1 cross S1 would be the product of a three-sphere times S1. And let's say if I talk about SU, if I'm studying SU2 Young-Mills theory, there are solutions which resemble these windings over the on the elliptic curve. Maybe these are solutions for which the gauge field has the form where G is the identification of the spatial S3 with the group manifold SU2, which is the gauge group. And so if you look at the ansatz of Young-Mills, SU2 Young-Mills fields, which you can actually now take to be SLC, SO2C, because F can be complexified, then for F you actually get precisely the harmonic, the anharmonic oscillator. So this is F squared 1 minus F squared potential. And so you get plenty of these solutions where you tunnel and you rotate, on this elliptic curve with various slopes. So maybe there is some algebraic integrability hidden in Young-Mills theory in the same way as is hidden inside the sigma model. So maybe there is an analog of finite gap. Okay. Okay, I'm sorry, I have to go now.
Okay, then more questions? And taking into account that Nikita is too late. Okay. Let's postpone questions to the next time. Thank you, Nikita.
Thank you. Thank you very much.
Спасибо.
Thank you. Bye.
Спасибо.